Okay, in this next segment, we're going to be talking about periodic trends, trends in the periodic table, and how we can explain them knowing the electron configurations that come from solving Schrodinger's equations and knowing the behaviors of the orbital. So learning objectives for this next segment: predict and rationalize trends in atomic size using knowledge about atomic orbitals, predict and rationalize trends in the ionic configurations. We've talked a lot about molecular configuration, about the elemental configurations, but what about when you lose ions? How do you understand those trends? And then predict and rationalize trends in ionic size. Once we know the electron configurations, how does the ionic size change? Okay, so reminder, since two electrons can't have the same quantum number, we fill up the orbitals one by one as we add one proton and one electron marching up the periodic table. Now that Aufbau principle before, when we're adding electrons in and the electrons add in those configurations, it's important to remember that when we go from, from nitrogen to oxygen, we're adding both a proton and an electron. So that electron both feels the influence of the other electrons around it, but also the influence of one more proton pulling it tightly in towards the nucleus. So that's important to remember in this next segment. And the rest of it is just quirks of which energy levels are lower as all the electrons interact with each other in the nucleus. You order up the energy levels. The only trickiness is where, because two energy levels are really close together, it's hard to figure out the ordering. The good thing is the big trends you can see just literally by looking at the periodic table. The 3D comes after the 4s instead of before the 4s. And the rest of the trends are in those anomalous electron configurations where you just need to remember that they exist so you can look them up later and check. Okay. So atomic radii, it's useful to know about atomic radii because that factors in significantly in ionic solids. And it's useful to just think about in terms of reactivity where the electrons are located around the ions. Okay, so here I've got a plot of the ionic radii for most of the elements in the periodic table, and we can see some definite clear trends here. It's not like completely obvious. The ionic radii does not strictly increase with atomic number, but there are some patterns we can explain knowing what we know about the orbitals and how they fill. Okay, so first we notice is as we go down a column, as we get bigger and bigger staying in the same column, the radius goes up. Now if we look from lithium, right, because as we go from lithium to sodium to potassium, rubidium, cesium, francium, we're just going down the group 1A, and the atomic radius always increases. And that makes sense. The outermost electron in lithium is a 2s, and for sodium 3s, potassium 4s, 5s, so on. And we know that as you get bigger and bigger, the s electrons are further and further out. Now, you've got the nucleus pulling in tighter and tighter, but you're always going to have an increase in size. Once you get out to really large sizes, it flattens off a bit. But once you go down a table, it is always going to increase in size because you're cramming more electrons in. Even though they're being pulled tighter in, the ones on the outside you're always adding in more bigger things. Okay, so as you go down a column, it holds true for the for halogens as well. As you go to having missing one atom in the shell, from fluorine to chlorine, bromine, iodine, it's going to be strictly increasing. So you can always be sure that as you go down the column, the size will get bigger. Okay, but then the other trend you notice is that as you go across a row, the radius goes down. Now this is a little less intuitive because you're adding more protons and more electrons, and yet the size is going down. Why is that? So the atomic radius is determined by the outermost orbital occupied. So, as we said before, as you go down, everything increases. It always increases no matter what row you pick. So yeah, increase going down due to increasing n, you get an additional outer shell. So the n equals 4 electrons are all out further than all n equals 3 electrons. The decrease across the row is due to the increasing effective nuclear charge, but electrons are filling the same orbitals as each other in the row. So, as we go across from, say, carbon, nitrogen, oxygen, fluorine, we're adding in more electrons, but all of those are 3p electrons, and the 3p orbitals all orbit in roughly the same size. Yet, so we're filling in orbitals that are of the same size, but we're adding more protons. And so those protons are pulling the p orbitals in. So even though we have more electrons, they're going into the same size orbitals and they're feeling pull from more neutrons, from more protons. Fluorine has more protons than oxygen does. So that's why that the size goes down across the row. As we go across the row, we're feeling the same size orbitals. We're feeling, the n orbital, they're feeling the n equals 2 orbitals or n equals 3 orbitals, which are all the same size, but we're adding more protons to pull those electrons tighter in. Let's take a look at just one example of phosphorus and sulfur. So phosphorus has 15 total protons, 15 total electrons. Sulfur has one more proton, one more electron, but it's smaller because that extra proton that's being added, the extra electron that's being added is added exactly to the 3p orbital, which is the same, all the 3p orbitals are the same size. That extra proton is pulling in all of the 3p orbitals. All the 3p orbitals are closer in. And so even though you're putting another electron in the 3p orbital, maybe it's providing a bit of repulsion to force the other 3p's away, but that's overwhelmed by the fact that you've added that extra neutron, that is extra proton, so that we're pulling all of the p orbitals in. Okay, so that's the trend. As you go across a row, the atoms get smaller, even though they're more massive.